Good morning everyone. Good to be back. Welcome to another video. Hope everyone's having a good day. What is it? It's July 14th, 2025. It's Monday today. Good to get into the spirit of things again. Feeling good. Hope everyone is alright. So I woke up this morning and had a slight bit of inspiration and a bit of a throwback to my younger days, I suppose. The subject of today is the Euclidean algorithm. An algorithm this algorithm is a method by which we can determine the greatest common divisor between two numbers. An algorithm itself being one that is with steps that are well defined, inputs that are defined, outputs that are defined. The steps themselves are deterministic, i.e. they use the same steps for each of the input, no funny business going on between. There are a finite number of steps, meaning there is a termination to the algorithm. There is a determined or an actual end point to this, at which point the algorithm stops doing whatever it is we tell it to do, and that is it. So in this case, our inputs are two numbers, i.e. the two numbers that we want to find the greatest common divisor of. And we do this in such a way whereby we define the A and B, but we care about the remainder, or what remains is when we divide A by B. And so once we define that remainder, then we can sort of shift B to be the new A and the R to be the new B. And we keep doing that. We keep finding remainders until we're all done, until there are no remainders left. Consider an example. Let's say 50 and 40. What's the greatest common divisor between them? Maybe there's a better example. 45, 30, I think, maybe. So 45, 30, 45 divides 30. Actually, that's not a good example. 50, 40. So 40 divides 50 once, remainder 10. Then 40, 10 we care about. So how many times does 10 divide 40? It doesn't matter. We don't care about how many times we divide it. 4, yes, but the remainder is 0, which means the greatest common divisor of 50 and 40 is 10. And hopefully I can prove that by the end of this. Going back, the algorithm itself, the Euclidean algorithm itself, is fascinating. The proof of which is rather involved and detailed, and it's quite long. Well, actually, no, it's not. The professor did it in the algebra class. He took about 10 minutes to do it on one side of a blackboard. If that could be hashed out in that amount of time, then maybe I can dedicate some time to it. Well, not here, but you can go have a read about it. I encourage you. It's a rather interesting topic. So we're back here in Programmers, the online C# version that we're using. It's not a computer algorithm. You can hash it out on a piece of paper with pen and paper, but it's an algorithm that we want to pass on the script here. Going back a bit, it was Ada Lovelace, or Augusta Ada King, Countess of Lovelace, who was credited with the creation of the world's first computer algorithm in about the year 1843. She lived 1815 to 1852. And so precise were her steps that I believe only a computer was sophisticated enough to carry them out. So she was credited with that discovery, the world's first algorithm. Unfortunately, she'd have to wait until 1944 when Alan Turing created the world's first computer, at which point we could then start putting some of these ideas, theories into practice. So let's get on. Let's do this. So let's create the Euclidean algorithm here in the C#. Let's clear the board. So let's start off. What do we want? Using system class program. Okay, moving on, and let's create this first loop. So, as always, as I go through these things, please leave a comment down below. Let me know what I'm doing right, or let me know if I can do things differently. Let me know your comments. So let's create this. So static void main. So as per last time, the void is not any particular instruction. The void is simply me giving a particular instruction for the console to output here on the right. So I'm going to define that. I'm not exactly telling it what to do first. The static itself is the group of instructions. The static is not an instruction, but the static is, from what I understand, it's the group of instructions and how they all interact together. So let's create that. So first of all, let's simply find a means by which I can interact with the output. Okay, so I want to be able to define what the A and the B are, or the inputs to this algorithm. So what is this? I want to write a line in the console. So enter the first number A, right there. Yeah, close that. Great. So I also want the same for B, so I'm gonna make a shortcut of it. I'm gonna copy and paste that at least, but make sure I get the right numbers in there. Oh, or the digits in there. So that will be your B. So here I'm defining a means for which A and B can be defined by me. Next would be some sort of logic here. A equals long dot try parse. Nope, I need try parse. And I'll explain this after I've written it. Not read line out comma even, no? Comma dot out long original A. Great, close it off, and I'm going to do the same down here with my B. Oops. Bool valid B. Okay. Yeah. So can I run this now? Great. So it's asking me what do I want to check? What do I want here? So there we go. We defined A and B. Oops. Have I got a spelling error first? It's very early in the morning here. It's I tried to do the things, but you can tell the mind is not entirely woken up yet. There we go. Okay, so that's it. We have A and B. Enter the first number A, enter the first number B. And so this will set the precedent for the rest of the algorithm, and we'll use these A and B as the inputs going forward. And what I've done here, the console write line is, as you can see here, what do you want the first line to be? The valid A here is a check that I'll incorporate later. We want to see if the A is actually a valid number. Maybe I put an alpha character in there, maybe, or a comma even. The bool will set up later for a binary check, yes or no. I haven't done that yet. And this whole long try parse here is, I had a bit of problems with this earlier. If I used the classic int syntax, it doesn't recognize really long integers here. And I should specify the Euclidean algorithm is, I suppose, for integers, not necessarily numbers. We can't use decimals here to find for the divisors here. It's strictly integers, positive, I believe. So the long try parse is in essence saying let's try and push this to the max. So all numbers of all digit lengths will be able to work here, and the try parse is effectively linking with that long to allow all those digits to be outputted. So let's go on and see if we can implement that check. So if valid A, same again, if valid B, cross it off, another loop. Thank you. Console.write line, and I'll explain this again. So I want the space n if it's an error 1 or both of the numbers entered are too long or invalid. Okay. Close that off. Otherwise, if it is valid, then simply return it in the console. So the if here, this is what's going on here. The exclamation mark means negation of. So if either one of the A here is invalid or the B is invalid, then let me know here. It's invalid or too long. So can I do that again? Yep. Some random number. Well, you can't have a 0 here. Both seem valid. Output. No, it's not linking here. Something. It's gone wrong. If. Okay, so I suppose this is what the next part is about. Yeah. Try it again. Oopsie. First B. Okay. I have a problem. Okay. I think I tried to run them concurrently. Good, they seem valid. No return. So they're returning them. It's not saying that anything's invalid. Good. Right, so let's move to the next part here. What is our next part here? Great, so we want to create the algorithm itself. So let's take a moment here. I've forgotten to talk about the most important part of this all. Euclid himself, Greek mathematician born in Alexandria, Egypt, I believe 300 BC. He is considered the father of geometry, creating the foundations for Euclidean space, flat space, straight lines, planes. So that's the axioms that he drew up, Euclidean space. I suppose that the father of geometry, but I suppose here he is maybe had a few moments spare on a Saturday or something, and he thought let's delve into the subject of coprimes and divisors here. So he, as you would, had a bit of spare time, created the Euclidean algorithm here, and graciously named it after himself. Let's create this algorithm. Where do we want to start? Okay, let's recall both the a and b. So long again, original a, and the long b equals the original b. Okay, so console write this again. The console write line is not a particular function in and of itself. It's simply communicating with the console, telling that what do I want it to output. So here we're stating the goal, right? So what is the goal of all this? We want to find the greatest common divisor of a and b. Greatest common divisor, the GCD, so we don't have to write that again, of, and here we're recalling a with the curly brackets, not square brackets, that's definitely not going to help, be using the Euclidean algorithm. Euclidean algorithm. Okay, close that off. Close that off. There you go. Okay. So, what is the algorithm? So, let's define some steps. The steps being integers, starting from the first step, and this will run as long as we have a non-zero remainder. So, I'm gonna run that out. So, what does that mean? B, B0. So remember the negation. So as long as b is not equal to 0, will be, I suppose, a de facto remainder as we keep going down the algorithm. We haven't defined that yet, but that's what it means. We will keep running this until b is equal to 0. Okay, but while it's not equal to 0, how are we defining this? So let's get the long remainder. What exactly is the remainder here? And that will be the remainder of when we divide a through by b. So notice here I'm using a percentage here instead of a, what is it, the forward slash, the backslash, forward slash, whichever one it is. Comments, help me out. We only want that remainder, okay? And that remainder is what we'll become the focus of moving forward. The focus of the algorithm moving forward. So right line again. So output each step. For what step are we working on? Curly brackets. Recall the step. Okay. A mod b. I'll explain that. B mod equals whatever the previous remainder is. Remainder. Yep. Okay. So. And this is the step here. This is modular arithmetic here. So we don't care about how many times b divides a. We are simply saying we want the remainder. So discard the actual number of times it divides it by, but we only want to find the remainder. Not a good way to explain this. At which point a will become the new b. No, b will become the new a, and b will be that remainder. Remainder. And this will keep going for as long as the step count is greater than 1, but until b eventually equals 0. We get a 0 remainder. So other uses for the modular arithmetic, amongst many, is to determine what day of a particular date it is in the future. Monday, Tuesday, Wednesday, etc. That's what this was used for. I'm not sure if Euclid knew this at the time. I don't even think they had days back at the time of Euclid. I don't think we were using what was it? Monday, Moon Day, Tuesday, Thursday, Day, Wednesday, Odin's Day, Thursday, Thor's Day. I'm not sure those characters in Norse mythology were around at his time, or even the Romans, Lunadi, Mercolody, Vendredi, etc. Anyway, I digress here. But this was not information that I was given in that lecture theatre that day, so I too was struggling. What are the real world applications for this? I digress. Let's carry on. Let's run this. Does this still work? No. Why not? Have I missed a... Okay, time, error, expected. Yeah, so have I concatenated something correctly here? Or have I used a semicolon instead of a colon, maybe? I'm going to tell me what my steps are. Finding console right line. See, everything was working up until this last point. Console right line. Okay. Yeah, console right line. A.b. Okay, so what is it? Hang on, can I scratch some of these things out? What am I missing here? Yep, so you're fine. Int step? Okay, what about you? Are you correct? No, why is that? Okay, maybe because I haven't defined while int step is equal to 1. Go. Is equal to b. Is equal to b. Have I spelled something incorrectly here? No. No, what is the problem here? I've done something really wrong. 1 second. I see now, sorry, I forgot to put the semicolon at the end of the step, okay. Okay, so let's try that again. If I put 2 random numbers in there, what do I get? Should I get something here? Okay, there we go, that's it. Code execution successful. So to find the greatest common divisor, the GCD of that number and that number, Euclidean algorithm, you can see this is how the steps go. The first number B is moving down in step 2 is the new A, the remainder 7, 11, 4, 4, 2 is going to be the new B, and we keep doing this, we keep finding the remainders until eventually we get a remainder of this 2 here, the last non-zero remainder. So that means the greatest common divisor is 2. So let's go back to my earlier example here. What did I say? 50 and 40. 50 and 40. Yeah, 10. So 10 is the greatest common divisor there. I was trying to say something earlier, but I was getting a bit lost with my own numbers. What is it? 45 and 30? 45 and 30, yeah. 15, what about 40, 20, 20, 40? Yeah, 40 and 30 even. What would that give me? I think that would still give me 10. No, okay, oops. I hit a backspace. 40, okay, 40 and 30. Great, 10. So we've got some higher divisors there. 20 will divide 40 and 15 will divide 30, but they are not common amongst 40 and 30. 10 is, and it's the highest of them. Good, let's close this off. Let's, it's not saying what the actual lesson is here, so let's finish that off, and I will provide that ending disclosure there. So what do we want? We want final console write line, and I'm going to, in essence, have the script say what exactly is the point of this. What is the lesson here? So as long as as long as the A is equal to 1, then the greatest common divisor is 1. Okay, and so it all centers around that. Console dot write line that. So what is the message here? If that is the case, if A is equal to 1 at the very end, then the greatest common divisor, spelled correctly probably, greatest common divisor, the GCD of the original A, yeah, and original B. Original, that's not going to work. Original B is 1. Close that off. Okay. So, and then I wanted to actually write that as well. Console dot write line. What's it? Hence original. No. Oh, I lost that. Yeah. Okay. Hence original A and original B are co-prime. Okay, and that's what it means to be co-prime. They have no greatest common divisors amongst them except 1. 1 is the highest thing that will divide them both. Okay, otherwise, what happens otherwise? Otherwise, we actually have a greatest common divisor. So otherwise, console.write line, and just output the greatest common divisor is, so I'm going to copy that because I know I'm going to get some spelling wrong here. Yeah, the greatest common divisor, the GCD of A is whatever that A is. So what is that final A? So what is that A calling? So remember, it's somewhere between these steps. That final A would be, it's stored in memory, isn't it? So A equals B will constantly update at each step until eventually the B becomes 0. But the loop, the loop is simply remembering what is the last non-zero remainder. So at which point, yes, the A holds on to the last non-zero remainder, which will be the GCD. So that is what that A is recalling down there. So I believe we're done here. So I'm going to write that out again, and I think we'll get that error message. So I'm going to make this a bit, okay, and let's try something hopefully a bit smaller. 64. What is that? No, the greatest common divisor GCD is Euclidean Algorithm. Oh, okay, so that's interesting. So I didn't plan for that one. So what is that? 879872. How many is that? Divided by 64. Oh, so 13,748 multiplied by 64 equals 879,872. Okay, great. The message seems to be outputting here. I've used my calculator here to figure that one out. Run again. Can we try another? 4. Okay. 68. I don't know. There we go. Okay, so 2. I was hoping we can find something with 4 or 8 or something as a greatest common divisor. Great, okay, well that's it. I think I hinted last time, if it's a number that ends in 2 or 4, or at least an even number, then it's not going to be a prime. But here, for the most part, not for the most part, but for any integer, if the sum of all the individual digits within the integer, or the integer is a multiple of 3, then it is divisible by 3. So that's interesting. Anyway, that's it. That's it. We've created a means for the Euclidean algorithm to be executed, testing it against 2 integers. So the steps, the Euclidean algorithm itself, again, you can do it on paper. These are the steps that you need, but we incorporated here programmers C# to execute this and make it a bit more streamlined, let's say. So I hope you enjoyed this. I hope this is informative for you, and if you're working on any of your own pieces that involve this, then great, hopefully this helps. And let me know in the comments, what did you think? If you enjoyed it, are you studying the Euclidean algorithm? Are you studying anything with divisors or anything in prime number theory? Let me know, I'd be happy to hear it. If there's anything I can do better, if I can collapse some lines, if there are better functions I can use. I didn't talk much about the int and the long trie-pass, but I had a bit of a problem trying to figure that one out until I eventually landed on the long trie-pass. But again, anything I could do better, anything I can add or something, please let me know. Happy to learn myself. Apart from that, it's Monday today. I'm going to attempt to upload this at some point later today. Yeah, apart from that, have a good day, everyone. Thank you for joining. Yeah, we'll see you at the next video whenever that may be. Thank you so much. See you soon.